Okay, students. So we are going to do the activity to show that pure substances can mix and form mixtures. For that, we need these materials. I have hydrated copper sulfate here. You can see the crystalline shape and the blue color nature of the hydrated copper sulfate. Then we have the naphthalene balls here and the mortar and pestle to grind the naphthalene into powder. Then again, since I am going to do both activities together, the first and the second activities, I have a beaker to which I will be transferring the substance and I have water to dissolve the mixture. And later to filter the mixture to separate the components or to observe whether we can separate the components. So first I will have to transfer the naphthalene balls into a mortar and pestle, and then I can grind it together. Grind it, or if I just press it itself, I can get the powder because it is a soft ball. We can easily powder it without any problem. Now students, you can observe these are two substances. One is the blue color crystalline powder and the other one is the white color crystalline powder. Now we have to mix the two powders. I will transfer it. Okay, to this I will add copper sulfate. Now I'll mix them both together. Now the two substances are mixed together completely. So here we have a mixture, but you can't really pick out the two substances. The naphthalene and the hydrated copper sulfate is visible to you. If it's not clearly visible, you can even use a hand lens and observe it more closely. Here again, you can see both the colors, but you can't really differentiate and separate them out. So this is a mixture. Mixture is a substance where more than one pure substances are mixed together and they exist together as one. So this is where you understand what mixture is. Then I will move on to the second part of the activity or the second activity in your textbook, where I will dissolve this substance. I will transfer it into a beaker. Transfer the mixture into a beaker. Now that I have transferred all the solid into the beaker, I will add about 50 milliliters of water. As you can see, this is a 100 centimeter cube beaker, a small beaker. To that, I will add about 50 milliliters of water. This is not a quantitative activity, so we don't have to measure the volume exactly. When I mix the components, you can see the solution becoming blue in color. And also at the sides you can see a white color solid remaining. Even in this you can see that there is white color substance that has not dissolved in water. So here students, you can observe that all the three components, water, copper sulfate and naphthalene are mixed together. So we have a liquid mixture. In that you can see the white color solid particles on top. Now what I will do is, this is a filter paper. I am going to fold the filter paper. I have folded the filter paper. I open it up and place it inside the funnel, and I will set a beaker under the funnel. Then if we put a few drops of water, the filter paper will stick to the funnel. To make sure that it sticks to the funnel properly. Okay. Now I can transfer the solution into this. So here I will filter this solution. You can see, students, this is how we set up to filter substances. A beaker is kept, a funnel is fixed to a stand so that you don't have to hold it, and there is enough space so the solution can flow down. Filter paper is there, that is the full funnel, and we have to make sure that the solution does not go out of the filter paper. It has to be within the filter paper. Here you can see the clear solution flowing down through the funnel and is getting collected in the other beaker. I will transfer. If I touch it to the wall, then it will flow faster. You have to make sure that you transfer all the components. Still the mixture is getting filtered. So you can see now all the solution has filtered. Here you can see the clear solution. It's a blue color solution. And inside the funnel I have solid substances left. So this is something that you can observe here. And this process where we filter this, it's known as the filtration process, and you all know it's a physical separation method. So if I transfer the solid substance that is there inside the filter paper onto this colored cardboard, we will have to really dry it and observe. For now, I will show you all that this is a white color solid substance. Remember, students, this is only for observation. We are not going to weigh the amount of substance. Otherwise, we will have to dry it completely and get all the solid here. Now here you can see this is only the white color solid. That means this is only naphthalene. And here as you can see, copper sulfate is blue color, and we have got the full copper sulfate into this beaker. First we had the two substances individually, copper sulfate and naphthalene. We mixed them together, got the mixture. Couldn't identify the components separately, then we dissolved it and filtered it, and by doing this physical separation, now we have the two components separately, naphthalene and copper sulfate. Even this copper sulfate can be poured into a large container, one that is flat but has a larger area. You can pour it into that, and if you allow the water to vaporize, then you can get the copper sulfate crystals back. So these are all physical methods of separation. From this activity, you all can understand, students, mixtures are made up of more than one pure components and it is mixed together, but when it gets mixed, the chemical properties, you can see the chemical property of naphthalene hasn't changed, chemical property of copper sulfate has not changed. So, chemical properties doesn't change, and also the components of a mixture can be separated by physical methods. Can you observe this? At the top of the mixture, you can see it more clearly. Although it's brown in color, the color is very much light at the top, and when you go down towards the bottom, you can see the color increases. And towards the bottom, at the bottom, you can see there are more solid components. But since this is a filtered solution, you can see the change in color gradually. So students, to confirm that the components are not distributed evenly, what we can do is we can take a drop of the mixture from the top as well as the bottom onto this metal foil, or you can use a metal plate. Here I will take a drop from the top and place it on this metal plate, as well as I will take a drop from the bottom of the mixture and place a small amount there. So, I have the 2 samples of mixture from the top surface on my left hand side and from the lower part of the mixture on the right hand side. So, if we take this metal plate and heat it, maybe using a candle, so then we can see how the particles are distributed in this mixture. So, let me do that now. So, now students, I have the plate after heating it. Now, you can see here, this side we don't see any mark. There are no soil particles here. Whereas in this side, the drop I took from the bottom of the mixture, you can see there is a small amount of soil particle remaining there. So, from this observation, there are particles of soil here, there is nothing on this side. So, from this observation, what can we conclude? If we take a unit volume of the mixture from the top surface and we heat it, then there is no soil particles. But from the bottom, when we take a unit volume of the mixture and observe the amount of soil particles present, we do have a small amount. So, that means the distribution of particles throughout the mixture is not uniform. It's less at the top and more at the bottom. That means this mixture is classified as a heterogeneous mixture. A mixture where the components are not distributed evenly, or the composition is not uniform throughout the solution, is known as a heterogeneous mixture. So, a mixture of soil dissolved in water is a heterogeneous mixture. So, here you can see students, a clear transparent solution is obtained when sodium chloride is dissolved in water. So, if the transparency, composition and color are all uniform throughout the mixture, you can observe that here we call it the homogeneous solution or homogeneous mixture. In other words, we can just call it as a solution. Okay students, so today we are going to observe how different solids and a liquid dissolve in water. So, to do this activity, I have different substances here. The sodium chloride, that is the normal salt that we use at home. Copper sulfate solid, you can see here. Then potassium permanganate solid, washing powder, and here is wheat flour and also ethyl alcohol. Out of all these substances, you can see the first 5 are solids. And you can observe the solids differently. This is a white color crystalline powder. Copper sulfate is a blue color crystalline powder, whereas potassium permanganate, that is Condis, it's a black color or very dark purple color which looks like black, and that is also crystalline. Then we have the washing powder and flour. These are substances that are used at home. Then we have the colorless liquid, that is ethyl alcohol. Now, I have already dissolved all these substances in equal amounts of water. Here you have to observe how the solution is. Look at the transparency and the color of the solution. So, let me show you. Here you can see this is sodium chloride. The solid sodium chloride dissolved in water gives a clear solution. So, the transparency is there. It's a transparent clear solution. Then we have the copper sulfate solution. Here you can see that is also a blue color transparent clear solution. Again we have the third solution here, that is potassium permanganate dissolved in water. That is a purple color clear solution, and that is also transparent. Then we have the next one, that is washing powder. Here you can see, students, at the top you can see the foam. Here the solution is almost clear, but towards the bottom you all can observe that there are particles remaining. That means the transparency and the color are not uniform in this washing powder mixture. We have the other solid, that is wheat flour dissolved in water. Here again you can see at the top it's very much almost clear, and towards the middle part of the mixture you can see there is a pale color, and at the bottom you can clearly observe that there is a solid substance present. So that means here the distribution of the solid is not uniform, and the transparency of the solution is also not uniform. Then we have the ethyl alcohol dissolved in water. That also you can see is a clear, uniform, transparent mixture. So, if you look at all these solutions clearly or the mixtures clearly, you can see sodium chloride mixture, copper sulfate solution, potassium permanganate solution, and ethyl alcohol mixed with water. They all have uniform transparency and the color is also uniform. But if we take these two, that is the washing powder dissolved in water and wheat flour dissolved in water, the transparency and the amount of substance present throughout the mixture is not uniform. So, this is how we classify these mixtures. These three which have uniform transparency, that means the solutes or the components are distributed uniformly throughout the mixture. Then we call them as homogeneous mixtures. Whereas the washing powder and flour mixtures, there the distribution of the components is not uniform throughout the mixture. So, we call them as heterogeneous mixtures. So, from this activity and from these observations, you will be able to identify clearly what homogeneous mixtures are and what heterogeneous mixtures are. So, you will be able to classify these mixtures easily. Okay, students. So, now we are going to see how the solubility of different solutes vary. To observe that, we have to do two activities where we use the same solvent that is water, and the same volume of the solvent, 100 centimeter cubes or 100 milliliters of water. To that, we add two different solutes. One is sodium chloride, common salt, and the other one is calcium hydroxide. So here you can see both are solid components, and this is 100 grams of sodium chloride. Here I have 10 grams of calcium hydroxide. So first I'll take equal volumes of water using the measuring cylinder. I can measure 100 centimeter cubes of water. Okay, so I have the 100 centimeter cubes of water in both beakers. So to the first beaker, I will add sodium chloride. So I'll take 1 teaspoonful of sodium chloride. We will dissolve it well. You all are familiar with this observation. You know that sodium chloride can dissolve well in water. So to this again, I'll add another spoonful of salt. One more. I will leave this solution to stand for some time, and with that time, if there is any more solute, that will also dissolve. If not, before comparing the results, we can dissolve it again. At the same time, I have the second solute, that is calcium hydroxide. Again, I will use 1 spoonful of calcium hydroxide and dissolve that. Here also you can observe as if the calcium hydroxide is dissolving completely. But you can see a difference in the two solutions. The sodium chloride solution is clear. It's a transparent solution, whereas here you can see the calcium hydroxide is not transparent. It's a milky color solution. So since I added 3 spoonsful of sodium chloride to this, I will add another 2 teaspoonsful of calcium hydroxide into this other mixture, so that we can easily compare the nature of the two mixtures. There is a little bit more of the sodium chloride that is not dissolved. So I am dissolving that as well. So now students, I dissolved 3 teaspoons of salt into this solution and 3 teaspoons of calcium hydroxide into the second beaker. The solvent is the same, water, volumes are the same, 100 milliliters of water, but the solutes are different, sodium chloride and calcium hydroxide. We can also do this activity by weighing the solutes and comparing the total amount of solute that can dissolve in water. But here I am going to compare how the same amount of solute dissolves in the same solvent. So here you can see in both we got clear solutions first. The sodium chloride is transparent and clear, but here when I mixed calcium hydroxide into water, it became a milky solution. Now that I have kept it for some time, you can see still the sodium chloride solution is clear and transparent, and all the sodium chloride solid has dissolved in water. But if you look at this calcium hydroxide, you can see that the solution is changing. At the top, the solution is becoming more clear, and at the bottom, although initially it looked as if calcium hydroxide dissolved in water, now you can see the solid depositing at the bottom. So from this, what can we infer? More sodium chloride will dissolve in water. Very less amount of calcium hydroxide dissolves in water. Now here we took 100 grams of sodium chloride and only 10 grams of calcium hydroxide. Even if I put some more sodium chloride and dissolve it, you know that it will dissolve in water. So obviously more amount of sodium chloride dissolves in water compared to the calcium hydroxide. So from this we can confirm that the solubility depends on the nature of the solute. That is one. Further, if we take these two solutions and heat them, I am sure you know what will happen. There will be more solute that dissolves in water. So when we increase the temperature also, we can increase the solubility of these two substances. Okay students, now again we are going to observe the effect of nature of solute on solubility. So to do that, we have two different solutes. One is sugar, the other one is salt. And we will have to take equal volume of the solvent, that is 50 centimeter cubes of water. So first I will take 50 centimeter cubes of water to both the beakers. So I have 50 centimeter cube of water in one beaker and to the other one as well. Okay. So now we have equal volumes of water at the same temperature. So solvent is the same, the temperature is the same. Only difference is the two solutes. So first I will dissolve sugar. So if I start dissolving sugar, we have to start with 1 teaspoon. We have to add it little by little and dissolve it. Similarly, I'll give it some time to dissolve. I will take the same amount of salt and dissolve it in water. So you can see when both the solutes dissolve, we get clear, transparent solutions. Okay. Now I am going to add another spoonful of both the solutes, sugar and salt. So I am just doing this activity to observe how different solutes dissolve in the same solvent, to compare the solubility. So like this, we have to add more solute and dissolve them in water until it comes to a point where there is no more solute can dissolve in water. So students, when we keep on adding the two solutes, sugar and salt, you can see they dissolve in water. And here we have a completely clear solution of salt solution, and still there is a small amount of sodium chloride remaining in it. So when we do this activity, if we initially weigh the solute, that is the sugar and the salt that I already did, it was 50 grams of both the solutes. Then we keep on adding them until the point where the two solutes don't dissolve anymore. After that, if you weigh the remaining solutes, then you will know which dissolves more. So this is an activity where you have to try this at home and find out what dissolves more. Okay students, now we are going to do this activity to observe the effect of nature of solvent on solubility. So here the room temperature is the same and I have the same solute, sugar, and I have weighed 5 grams of sugar and taken it in filter papers. And here I have two different solvents of the same volume, 50 centimeter cube of water and 50 centimeter cube of kerosene. So the volumes are the same, only difference is the nature of solvent. So to the first solvent, I will add the 5 grams of sugar. Completely we have to add it and I have to dissolve it. At the same time, I will add the 5 grams of sugar into water as well. And I will try to dissolve that also. So here you can see it's only 5 grams of sugar. I will try to dissolve the sugar in water. You can see it dissolving and you can see it's a clear transparent solution. Same way I try to dissolve sugar in kerosene. Already you all can observe a small difference in the solubility. You can see sugar is dissolving fast in water, but almost all the sugar is remaining in kerosene. Nothing seems to dissolve in kerosene. So here almost all the sugar is dissolved in water. A little bit more sugar is there. Yes. So now the sugar has completely dissolved in water. Okay students, you can see here the 5 grams of sugar has dissolved completely in water, but almost the 5 grams of sugar still remains undissolved in kerosene. So from this observation, you can see the solid sugar crystal still remaining here. So students, you can see 5 grams of sugar has dissolved completely in water, but almost the 5 grams of sugar remains undissolved in kerosene. So here we had the same solute under the same temperature, but the solvents are different. Water can dissolve sugar well, whereas kerosene cannot dissolve sugar. So that means the solubility of a substance depends on the nature of the solvent. Okay students, now we are going to test or demonstrate how pressure affects the solubility of gases, or we will check and see whether pressure affects solubility of gases. Now I have two identical plastic bottles So we can press it and try to squeeze it. Here this is a sealed bottle of aerated water and this is an open bottle filled with water to the same level. So everything is same except that this is an open bottle containing water and this is a new bottle of aerated water. So what I will do is I will try to press the two bottles from the bottom. If I press, you can see the bottle that contains water gets compressed a little bit. But I apply the same amount of force, but I am unable to press it and compress the bottle that contains aerated water. You all know the meaning of aerated water. There is carbon dioxide dissolved in this water. That is why we call it aerated water. So when there is carbon dioxide dissolved, we can't press it. So this is one observation. The reason for this is this carbon dioxide gas had been dissolved in this water or in this solution, aerated water, under high pressure. And since I have not opened the lid, still it is under high pressure. So I am unable to compress this bottle, but I can compress the second bottle. Here you can see if I open this also, there is no evolving of gas. It's the same liquid water. Now I will open this bottle. You all are already familiar with homogeneous and heterogeneous mixtures. This is a homogeneous mixture at the moment because you can't differentiate between the water and the carbon dioxide dissolved in it. Now I will open this bottle a little bit. Now you can see the gas bubbles coming up. So now it becomes a heterogeneous mixture. Why? You can see the gas bubbles coming up. I will open it a little bit more. What happens here when I open the lid? The pressure is released, and because the pressure is released, the solubility of carbon dioxide decreases. Therefore, the dissolved carbon dioxide is being released from the solution. I will open it further. Here still you can observe the evolving of gas. Okay. So I will leave it like this until all the gas evolves. So here you can see when the pressure was released, the homogeneous mixture became a heterogeneous mixture. Now I will squeeze both the bottles. Now you can see still I can squeeze this nicely, whereas I can squeeze this to a certain extent more than the previous instant. Earlier when it was completely sealed, I could not press it, but now I can press it. So that means the pressure has been released. So from this observation, students, you all observed two main things. A closed sealed bottle of aerated water is a homogeneous mixture, but once you open it, you can see the gas bubbles, that is carbon dioxide gas. So it is a heterogeneous mixture. And that gas, that is carbon dioxide, was completely dissolved in water due to the high pressure. So we can conclude that the increase in pressure increases the solubility of gases. Okay, students. So we are going to do this activity in order to observe the composition of mixtures. So for that, I have the same solvent and solute. I have here 100 centimeter cubes of water. Although we were supposed to take 50 centimeter cubes, in order to show you all the color change or the difference in intensity of color, I have taken more water, but in both the beakers, I have equal volume of the same solvent water. And here again, I have a very small amount of potassium permanganate and a larger amount of potassium permanganate. So, the same solute but different amount. Now, I will dissolve the smaller amount of potassium permanganate in water. So, here you can see it is a purple color solution. At the same time, I will dissolve the large amount of potassium permanganate, and when we dissolve that is also a purple color solution. But here you can see the difference in intensity of color. Although the solvent and the solute are the same and both solutions are at the same temperature, because I took less amount of solute, that is less amount of potassium permanganate, the intensity of the color of solution is less here. And when we take more solute, the intensity of the color is more. What is the reason? The reason is the amount of solute in a unit volume of solvent is less in this and more in this. So, therefore, the amount of solute present in a unit volume of the solution is very important to us. That is what we will be defining as composition. And to give compositions, we have different units. But students, you all can understand that the amount of solute in different solutions give rise to difference in composition of the solution. Okay, students. So now I am going to prepare a standard solution of sodium chloride. To do that, I have a wash bottle with distilled water, a volumetric flask. You can see it is a 250 centimeter cube volumetric flask. And here you can see the volume mark. We have to fill water up to this point so that we get exactly 250.00 centimeter cubes of the solution. Then I have the funnel to help us to transfer the solute into the volumetric flask, and also the solute is sodium chloride. We need to take 14.6 grams of sodium chloride in order to prepare 250 centimeter cubes of 1 mole per decimeter cube solution of sodium chloride. And as you know, students, we have to weigh the solute accurately. So to do that, I have the triple beam balance here. With the watch glass, I have balanced it to 0. So you can see the 0, the balance is at the rest. It's pointing to 0 with the watch glass. Now I need to set the value to 14.6 grams. So here 14.6 grams. So to that, if I add the sodium chloride, then we will be able to weigh 14.6 grams. We have to weigh the exact amount of sodium chloride. Now you can see the scale coming to a balance. If it points to 0, that means we have weighed 14.6 grams. So now I have the volumetric flask, a clean one. I will set everything so that I can easily transfer the substance. So here I have the funnel. I'll hold it slightly above the mouth of the volumetric flask, and to that I have to hold the solute containing watch glass in this manner, so that I can easily dissolve and transfer all the sodium chloride into the volumetric flask. So that is the use of the wash bottle here. We can make sure that we transfer all the solute into the volumetric flask. So here I have transferred the solute, everything from the watch glass, and I wash it with more water to make sure that all the solute is dissolved here. Now I have transferred all the solute into the volumetric, and also I wash the funnel again to make sure that all the solute is transferred into the volumetric flask. Now what I have to do is I have to add about 3/4 of the volume of water. Okay. Now I close the lid again just to make sure it's clean. What do? We hold the volumetric flask in this manner. Always you have to have a hand under the volumetric flask, and by swirling it, we can dissolve the solute. It has to be a swirling motion so that the solute dissolves completely. We shouldn't turn it upside down. So here you can see the solute dissolving. If we keep on swirling it like that, the solute will dissolve completely. I think all the solute is almost dissolved now. So that the solute is completely dissolved. Now I will make the volume up to the volume mark. So again I'll remove the lid and add more water. Up to a certain point you can quickly add water. Now it's almost closer to the volume mark. So my eye level has to be along the line, and here I have to make sure that I add the correct volume of water. You can see the meniscus here, students. The curve, the bottom line of the meniscus has to be in line with the volume mark in the volumetric flask. So I'll again make sure that I have added the correct volume, and now I can close the lid, and I have prepared the standard solution of sodium chloride. So students, now I have added the correct volume of water, and I have to make sure that the solute gets distributed throughout the solution. So to do that, again we have to mix the solution, but we have to be careful that the solution or the solvent doesn't escape from the volumetric flask. So when I mix it well like that, the solute gets distributed evenly. So we have a solution where the concentration is uniform. So that means we have prepared a standard solution with a known concentration. So once that is done, you can't leave it like this, because there are instances where many people work in the same lab, and you might need to make more than one solutions which look the same. So then we have to put a label for the solution so that we can identify the solution easily. And what do we include in the label? We have to write the solvent, the solute, the name of the solution and the concentration of the solution, as well as the date on which the solution was prepared. And to make it more clear, if there are many people working in the lab, we can also include the name of the person who prepared the solution. So then the label will have all the necessary information. So students, keep it in mind that when we prepare a standard solution, the measurements have to be accurate, all the glasswares have to be clean, and once we do the preparation, we have to label the solution. So here I have the standard solution of sodium chloride. I have to have a label on this. Okay students, so now I am going to demonstrate how we do the filtration process. To do that, I have 50 centimeter cubes of water here, and into that I am going to dissolve 5 grams of sodium chloride, and here I am going to show you all the technique. So I have 5 grams of salt dissolved in water, and also I will add about 10 grams of soil. So now you saw that it is a mixture that has water as the solvent and salt, that is sodium chloride, and soil as the two solute components. So now we have a mixture in which we have the two solutes. So now I am going to carry out the filtration process. For that, I have the setup here, a conical flask to collect the filtrate. You can remember the term, students. The solution that comes into the conical flask is known as the filtrate, or the solution that is filtered is known as the filtrate, and what is going to remain in the filter paper is going to be the residue. So inside the funnel, I will have to place a filter paper. I will fold the filter paper like this and place it into the funnel. So here we have to make sure the filter paper sticks inside the funnel. Then to transfer the solution, I am going to use a glass rod. If we hold the glass rod this way and pour the solution along the glass rod, we make sure that the solution doesn't spill. And also when doing this process, we shouldn't pour all the solution into the funnel. Little by little, we have to transfer the solution so that it gets filtered properly. Now here you can see the clear solution getting filtered. So when the amount of solution inside the funnel decreases, we transfer more solution. And again students, this is a mixed muddy mixture, whereas you can see here a clear solution getting filtered into the conical flask. So the filtrate is going to be a clear solution, and we will get a residue in the filter paper. I will transfer some more of the solution. So here students, you can see the solution flow. So along the wall of the conical flask, you can see the solution. Just to show you all that it is coming into the flask, I will move it a bit. Here you can see drop-wise the clear solution getting filtered into the conical flask. Again, I will push it back so that they are in contact with each other, and I'll transfer the rest of the solution. Okay students, now almost the solution has got filtered into the conical flask. So here you can see it is a clear solution that has been obtained inside the conical flask. So that is the sodium chloride solution. And here I have the residue. So here you can see the residue, that is the soil residue that has been filtered by the filter paper. So what remains in the filter paper is the solid component that has large particle size. So therefore it doesn't get filtered through the filter paper, and that is called the residue. And the solution containing the solute with smaller particles that can be filtered through the filter paper enter into the flask, and that is the filtrate. So this is the method of filtration where we have separated the components of a mixture. Okay students, now I am going to do the recrystallization process. To do this, I have the setup here with the funnel placed on the stand. Into the funnel, I need to place a filter paper. I have to fold it and place it inside the funnel. And also, I have already set the conical flask here so that it is easy for me to transfer the solution. So, the solution will be sodium chloride, that is the common salt, but here we have the crystals of salt, and I am going to dissolve that in hot water. This is about 90 degrees in temperature. So, to this I am going to add the salt and dissolve it. You all know that when the temperature of the solvent increases, the solubility increases. So, here we are going to dissolve salt in hot water. And during this process, we are going to remove the impurities present in salt and get the pure salt crystals. Okay students, so I have the salt solution dissolved here at 80 degrees Celsius. Now I am going to filter it through the setup. You have observed this before, the filtration process. We have the conical flask, funnel placed on the stand, and inside the funnel there is a filter paper. You have to fill the solution to about 3/4 of the filter paper so that it doesn't flow out of the filter paper. And when it is getting filtered, I can transfer more solution. So here now the pure sodium chloride solution is getting filtered. Impurities and the salt dissolves in hot water. So whatever that can be filtered by the filter paper will remain as the residue. Those are some of the impurities. Then all the particles that can go through the pore size of the filter paper will get filtered. We will collect the filtrate inside the conical flask. Once we do that, we have to place the conical flask inside the beaker containing ice so that the solution will cool and the crystals will form again. So now I have transferred most of the solution into the funnel. We'll have to wait till it filters. Now the solution has been filtered so that I can remove the conical flask and place it inside the beaker containing ice. I will hold it there so you can observe the formation of the crystals. Now you have to observe clearly inside the flask. Okay, students. So, I place the conical flask to which I got the filtrate of the solution that was kept inside ice so that the crystals will form. Now, I have transferred the set onto a black colored surface so that you can observe it clearly. I will take out the conical flask so that you can observe the crystals that have formed more clearly. So, here students, you can see the sodium chloride crystals. Only a small amount has been formed because during the process impurities are removed and also some of the crystals form on the way, that is through the funnel, and also there can be some crystals still remaining in the beaker. So, here what I have is the pure salt crystals. Impurities have been removed and only the sodium chloride has crystallized. So, this is the process of recrystallization, and we use this to purify solid substances or to remove impurities from solid substances. Okay, students. Now, I am going to demonstrate the technique of solvent extraction. So, here I have the separation funnel. You can see it's a glass funnel, that's called the separation funnel. It has a lid and it has this tap where you can open and close the tap so that you can draw solution through the separation funnel. And here I have a solution of iodine, that is iodine dissolved in water. So, this is the solution that contains our component, that is iodine. So, from water I need to extract iodine into another solvent. So, here I have carbon tetrachloride. You all already know water is a polar inorganic solvent, whereas carbon tetrachloride is a non-polar organic solvent. So, the polar solvent water does not mix with the non-polar carbon tetrachloride. And here you can see the color of the solution. It is light reddish brown in color. And here when I add some of the carbon tetrachloride into the separation funnel, you will see that it is a colorless solvent. So, in this we have to take two solvents that do not mix with each other. And also the solubility of iodine is somewhat less in water and it is more in carbon tetrachloride. So, that is how we are going to extract the iodine from water into carbon tetrachloride. So, now I will add a small amount of carbon tetrachloride into the separation funnel. You can see it is a So, now I have the solvent inside and I have to make sure the tap is very tight so that the solvent does not leak. Then I add a small amount of iodine in water. So, here you can see the different colors. Now, you can see as I add the iodine solution is brownish in color. We have the other layer which was clear has now become a little bit purplish in color. Now, what we do is we tilt the separation funnel and mix it in this way, and also we have to open the tap a little bit in order to release the pressure. Again we close and we mix it in this manner. This is the technique that we use to mix the two solvents in solvent extraction process using the separation funnel. Now I will open the lid and I will allow the mixtures to settle down. As you observe, you can see the separation of the two layers. Earlier, this was darker in color. The iodine in water was very much more brown. Here you can see the colors. Now it has become very light. And also the carbon tetrachloride was colorless. But you can see now it is purple in color, pink or purplish in color. So what we can do is, now we have separated the solute. That is, we have extracted some of the iodine into the carbon tetrachloride solvent. Now I will have to separate the two layers. To do that, I will open the tap. Only the pink color layer will flow into the conical flask. And when it comes to a point where this interface, the point where the two solvents meet, I will close the funnel. So here I have left a certain amount of that other mixture here so that it doesn't get mixed. You can even draw a little bit more of the carbon tetrachloride layer so that we have most of the iodine in the conical flask. In case you need to have the top layer, then you have to remove the bottom layer out first and then you can take out the top layer. So from this process, we can extract the solute present in one solvent into the second solvent. Okay students, so now I am going to show you all the process of simple distillation. I have prepared the setup for the simple distillation process. Here you can see there is a round bottom flask. Into this round bottom flask, we will be taking water. For this purpose, we will be using well water. So, there are other substances or salts dissolved in well water. From well water, we need to prepare drinking water or the distilled water. So, here it is placed on a tripod to hold the round bottom flask, and you can see the burner is placed under it. And if you go up a little bit, if you can observe clearly, there is an outlet for the steam to come out from the round bottom flask. So that is the point from which the steam will escape or come out of the round bottom flask when the solution starts to boil. At the same time, here you can see a stopper is attached to the round bottom flask so that the steam does not escape, and also there is a thermometer fixed to it so that we can observe the temperature of steam to make sure that only the water vapor is coming out of the distillation flask. And here you can observe the tip of the bulb of the thermometer is in line with the vapor outlet. So there you will be observing the temperature of vapor that is coming out. Then this part is connected to the condenser. This condenser is called the Liebig's condenser, and this is a tube inside and an outer casing, and also there are 2 points to send water in and to collect water out. Now to these students, if we send the water from the top opening, the opening that is here, what do you think will happen? This is placed in an inclination. There is a slope, a slant manner you can observe. So when we send water through the opening here, the water will flow very quickly and come out of the second outlet. So there water will not remain inside the condenser for a long time. That will not give efficient cooling. So what we do is we send the water from bottom so that water fills in the whole condenser and it comes out, flows out through the top opening. So that throughout the process there is enough water flowing through the condenser. The vapor can condense very easily, and the condensed vapor, that is the water here, will come out from this end, and we will collect the water here. So here we have the full setup. You know why we use the thermometer to monitor the temperature, and why we use the round bottom flask, that is the distillation flask, and Liebig's condenser to condense the vapor and to collect the pure liquid. And also you have to remember how water is sent into the condenser as well as how it is taken out from the condenser, so that we make sure there is enough uniform cooling. Now that the setup is ready, I will start the distillation process. So students, you can observe that the water has started boiling, and also if you observe the temperature of the thermometer, you can see it increases and it comes to a certain point and remains at that point. At that point, the water is boiling and the steam with that particular temperature will escape through this condenser, through this outlet, and go through the condenser. If you observe the condenser now, you can see water coming through it because the steam is condensing within the condenser and the liquid is coming out from the outlet. So this is how we obtain the distilled water. We had the well water here, we produce the steam, and from the steam we condense it and obtain the liquid water. So that will be the distilled water that is coming and getting collected in this beaker. So here you can observe the simple distillation apparatus that we use to obtain distilled water from using well water. Okay students, so now we are going to observe how steam distillation takes place. I have prepared the setup here. You can see the first round bottom flask, and there is a burner under it, and there's water inside, and a thermometer is connected here. So when we light the burner, due to the heat, steam will be produced. When water reaches the boiling point, it will start boiling and generate steam. And you can see here there is a tube, a glass tube. So the water vapor will enter the glass tube and travel into the second flask. At the same time, we can monitor the temperature reading using the thermometer. Here we have to make sure that the tube or the glass tube is somewhat far away from the water level, so that only the vapor enters into the glass tube but not the water that is boiling. So in the second flask, we have the plant from which we are going to extract the essential oil. Here I am using cinnamon leaves. So I will be extracting cinnamon oil. Then from this, through the first flask, steam enters into the second flask. So due to the heat of the steam, the volatile compounds that are present in the leaf will turn into vapor, and the vapor will escape through this outlet, and that is connected to the Liebig's condenser. As you already know, we send water through the bottom opening of the Liebig condenser and take out the water from the top opening. And you can see the condenser, it is kept at a slant position. There is an inclination there, so that water will enter from the bottom and fill in the condenser, and throughout the distillation process there will be water flowing continuously through the condenser. That is cool water. So because of that cool water, the normal temperature water, the vapor that enters into the condenser will condense and the liquid will be obtained from the outlet. So here we will be collecting the oil that has been extracted from these cinnamon leaves. That will be the cinnamon oil. So here we have to remember, students, that the cinnamon oil becomes vapor because of its low volatility. It's a highly volatile compound, so that means it can vaporize quickly and can be extracted. So as you already know, this process of steam distillation is based on the volatility of substances. Volatile substances are easily extracted using this process. So now that I have the setup ready, I will start the distillation process now. So students, now the flask is supplied with heat. So the water inside the flask will boil and steam will be generated. And as you know, the steam enters into the second flask where we have the cinnamon leaves. So the steam makes the cinnamon oil present inside the cinnamon leaf to vaporize, and both the steam as well as the oil vapor mix together and they exit through the outlet of the second flask. And when they enter the condenser, as you know, due to the water flow, there is a cooling process taking place. Therefore, the vapor mixture will condense, and from this side, the outlet of the Liebig's condenser, we will be able to collect both water as well as cinnamon oil. So, as you know, cinnamon oil and water don't mix. They are immiscible liquids. Therefore, when we collect the output or the liquid that is coming from the outlet, the cinnamon oil and water will separate into layers. But for the full process to happen and for us to collect a large quantity of the two, we need to continue the process for a long time. Now, of course, you can see the water boiling. So, the steam is passing through and here you can see there is the liquid coming out. Since I am doing the activity, I can feel the smell, I can get the smell of cinnamon oil. But here you cannot see the two layers separating because of the small volume that has been collected. If you need to observe the separation of the oil and water layer, we have to carry out this activity for a longer period of time. So here the main aim is for you all to understand how the setup is connected and how the steam distillation process takes place. Okay, students. So now I am going to demonstrate the chromatography technique. So we will try to see how chlorophyll, the green pigments present in leaves, are separated using this method. So for that I have already grind some leaves. These are ground leaves. From that I have to take the juice. So to get the ground juice from the leaves, I have to filter it using a cloth. So what I have to do is, what I have already ground into a paste kind of mixture, the pulp, I will transfer onto this cloth and get the extract from it. So here I have the ground leaves. If we take the extract from it, you can see it is a nice green color extract. So from this extract, I have to make a spot on the chromatography paper. You know what a chromatography paper is. I have got it ready here. You can see it's connected to a cork and you can see the shape of the chromatography paper. Here it has a sharp point, and for this purpose there are chromatography papers available in the market, or we can use a blotting paper, or even the filter paper can be used for this purpose. So on this, first I have to make a spot of the sample. To do that, I have a petri dish here. I'll place the chromatography paper on this. So to make the spot, normally we use a capillary tube. Here I'm going to use a very thin drop using the pipette. So I'll try to make a very tiny drop using this. So here you can see it's a very small drop. It would be better if you can make a tinier drop using a capillary tube, and we have to allow it to dry for some time. So here it's already dried. If the concentration is not enough, if there isn't enough sample there, then we can put another drop, but here the sample is sufficient. So now I have to get this into the chromatography setup. Now, as you know, students, already the chromatography depends on a mobile solvent or a mobile phase which moves along the stationary phase. Here we have the stationary phase, that is the paper, chromatography paper or the blotting paper. And I am going to use acetone as the mobile phase. So I will have to take the acetone into a boiling tube, but I have to make sure that there is enough acetone so that I can slightly dip this. The paper has to slightly touch the acetone. Too much is not good. At the same time, we should have enough acetone to be in contact with the paper. Now the tip of the paper is in contact with the acetone solvent, and you can see the solvent rising along the chromatography paper. So with the solvent, the pigments present in this chlorophyll extract will also rise along the paper. You can see the green color moving upwards. So there the pigments that are present in the extract are getting separated. You can see the movement of the green color. Observe clearly, students. You can see the movement of the green color pigments along with the solvent. And as you know, acetone is a volatile solvent or a volatile liquid. So it also vaporizes and saturates the container, that is the boiling tube here, so that the solvent, when it is moving upwards, doesn't spread throughout the paper. So again, you can observe the movement of the colored pigments. There, the different components get separated along the way. Okay, students. So from this activity, you have observed the stationary phase, that is the chromatography paper or the blotting paper, as well as the mobile phase that I used here is acetone. And the separation is for the chlorophyll pigments. And you can see the movement of the green color. So this technique also can be used